think about all the sounds around us. I mean, really think. The school bell, music, cars honking, voices, even animals. It's just everywhere, isn't it?
It really is. Sound is such a fundamental part of how we experience the world.
And that's what this deep dive is all about. We're going to, explore the science behind what we actually hear.
Exactly. Our mission today is to really get under the hood of sound, understand where it comes from, how it gets around, what makes different sounds. Well, different. We've got a bunch of info to draw on.
Okay, so let's get right to it. Where does sound even begin? What's the starting point?
Well, it all comes down to vibration. Basically, sound is a form of energy that our ears pick up.
Right.
And that energy almost always starts with something moving back and forth really fast. Vibrating.
Okay, vibrating. That quick sort of shaking or trembling, yeah. Like when you pluck a guitar string?
Precisely. That rapid movement, that oscillation, that's the key. I mean, even think about your own voice right now. The sound you're making happens because your vocal cords are vibrating really, really quickly.
Right. And the sources we looked at had some good, clear examples, like a bell ringing. It's not just making noise. It's actually physically vibrating.
Yeah, exactly. Or that guitar string, like you said. And there were those activities, too.
Oh, yeah, the activities, like the hacksaw blade clamped to a table.
Activity 1, you flick it, you see it wobble back and forth. That's the vibration, and you hear a sound.
Simple, but it shows it clearly.
And activity 2, the stretched rubber string, you pluck it, you see it move, you hear it. It's that direct link.
And the tuning fork 1, activity 3. That was interesting because you strike it, and the vibration is so fast you might not even see it clearly.
Right, but you can definitely feel it buzzing if you touch the stem, and you hear that very pure tone.
Yeah.
And that activity even showed how the vibration carries energy. Remember the part about touching it to water?
Oh, yeah, it made ripples.
Exactly. Shows the vibration moving the water. And the table tennis ball.
It knocked it away.
Yeah. So that vibration is transferring real mechanical energy. It's pushing things.
So the takeaway is no vibration, no sound. It's that fundamental.
Pretty much.
Okay, so something vibrates, sound is produced, but how does it get from, say, that vibrating guitar string over to my ear? What's the journey?
Okay, that's where the idea of a medium comes in. Sound waves. That's the vibrating energy moving along. They need something to travel through.
A medium. Like what?
Like a solid, a liquid, or a gas. Think of the particles in that substance. The vibration gets passed from one particle to the next.
Okay, so for most sounds we hear every day, walking around, talking, the medium is just air.
Air, exactly. The vibrating object bumps the air particles next to it, they bump the ones next to them, and so on. It's like a chain reaction carrying the energy outward.
Okay.
But, and this is really important, sound cannot travel through a vacuum.
A vacuum, like empty space, outer space.
Exactly. If there are no particles, there's nothing to vibrate, nothing to pass the energy along. Sound just stops. Activity 4 showed this really well. The electric bell in the vacuum jar.
Right, they pump the air out.
Yeah. And even though you could see the little hammers still hitting the gong inside, the sound got fainter and fainter.
Until you couldn't hear it at all.
Correct. Proves you need that medium, in that case, the air.
Well, and didn't the sources mention something about the sun? How it's incredibly loud inside, but we don't hear it?
Yeah, that do you know fact. Massive sound energy produced by the sun, but the vacuum of space between us, and it means none of that sound reaches Earth. Silence, thankfully.
Imagine if it did. So the medium is essential. Now, you said solids, liquids, gases. Does sound travel the same way, same speed through all of them?
Good question. No, it doesn't. The speed changes depending on the medium.
Okay.
And generally, sound travels faster through denser media.
Denser, so faster through a solid than through air.
Usually, yes. Think about that classic example. Hearing a train coming by putting your ear to the track.
Oh, right. You hear it through the metal rail before you hear it through the air.
Exactly. Because the steel rail is much denser than air, the sound vibrations travel through it much, much faster.
That makes total sense. And activity 5, the clock on the table 1.
That showed sound traveling through the solid wood of the table. You press your ear against it, you hear the ticking better than through the air alone.
Okay. And liquids. Activity 6 used a water balloon.
Yeah, a balloon filled with water and a ticking watch inside. It showed sound traveling through the liquid. And activity 7, striking metal rods underwater.
It said the sound was louder underwater than in air.
Right, suggesting water is actually a pretty efficient medium for sound, better than air in some ways.
So solids generally fastest, then liquids, then gases like air are the slowest? Is that the rule?
That's the general trend, yes. Now, thinking about air specifically, how does it work? It travels as waves of compressions and rarefactions.
Compressions and rarefactions. What are those?
Okay, imagine one prong of that tuning fork again, like in figure 3.8. When the prong moves outwards, it pushes the air molecules close together. That's a compression, higher density, higher pressure.
Okay, squishing the air.
Sort of, yeah. Then, when the prong moves back inwards, it leaves a space where the air molecules are more spread out. That's a rarefaction, lower density, lower pressure.
Stretching the air?
Kind of. And it's this pattern of squish, stretch, compression, rarefaction that travels outwards from the source as the sound wave.
So it's like a pressure wave moving through the air.
Exactly. A wave of changing pressure. And it spreads out, too. Think about figure 3.10, the school bell example.
Right. You can hear it all over the playground.
Yeah. Sound radiates outwards in all directions from the source.
And the sources gave actual speeds, didn't they? Like 332 meters per second in air?
Roughly, yeah. And much faster in water, about 1,440 meters per second. And then in something really dense like iron, it's incredibly fast, around 5,000 meters per second.
Well, that's a huge difference, 332 versus 5,000.
It really is. And it explains that train track phenomenon perfectly, the calculation example they gave with the gunshot.
Oh, yeah. Hearing it 2 seconds later from 660 meters away?
Right. If you calculate that out, distance divided by time, 660 divided by 2, you get 330 meters per second. Pretty close to the standard value for air. Shows how you can figure out distances using sound speed.
Okay, that makes sense. So we've got vibration creating sound and a medium carrying it via these compression rarefaction waves at different speeds. But, not all sounds are the same type of sound, are they? Like music versus just noise. What's the science behind that difference?
That's a great distinction. The core difference really lies in the nature of the vibrations producing the sound.
How so?
Well, musical sound usually comes from what we call periodic vibrations. That means the vibration happens in a regular repeating pattern over time.
Periodic. Like predictable.
Exactly. Think of a smooth repeating cycle. This creates a sound wave with a regular, often smooth pattern too. And our ears and brain tend to interpret that regularity as pleasant or musical, like a note from a flute or someone singing a clear tone.
Okay, so music is orderly vibration. What about noise then?
Noise, on the other hand, comes from non-periodic vibrations. Irregular, chaotic, random fluctuations.
So unpredictable vibration.
Pretty much. This leads to a sound wave that's jumbled, messy, with no clear repeating pattern. Think of dishes crashing, or static on a radio, or heavy traffic. We usually find these irregular sounds unpleasant or jarring.
So it really boils down to the pattern.
Yeah.
Organized and repeating for music, random and messy for noise.
That's the essence of it. And Table 3.1 laid this out nicely, comparing the waveform, the type of vibration, even the effect on our ears and mind. It mentioned decibel levels, too.
Right. That table was helpful. It showed the contrast clearly. And Activity 9, the tuning fork making waves in water again.
Yeah, that's a good visual. Those regular, consistent waves spreading out that represents the kind of organized pattern you get with a pure musical tone.
Okay, interesting. Let's dive a bit deeper into the sources themselves. Where does sound actually come from? We've mentioned vocal cords, instruments.
Yeah,
What else?
well, we already talked about the tuning fork quite a bit, that U-shaped metal thing. When you strike it, it vibrates at its own specific natural frequency. Very precise. They're often made to match musical notes, and the frequency is usually stamped right on it.
A very pure sound source. What about actual musical instruments? The sources group them, right?
Yeah, into stringed percussion and wind instruments, and reed instruments too.
Let's start with strings.
Yeah.
Violin, guitar, piano.
Okay, so with stringed instruments, the sound starts when the string itself vibrates because it's plucked or bowed or struck like in a piano. And often the instrument has a hollow body, which acts like an amplifier. It resonates with the string's vibration and makes the sound louder.
And it can change the pitch, right? Make it higher or lower.
Absolutely. You change the pitch by changing how fast the string vibrates. You can do that by adjusting its length, like pressing down on a guitar fret, or its thickness, or how tight it is.
Yeah.
Shorter, thinner, tighter strings vibrate faster, giving you a higher pitch.
Makes sense. Like tuning a guitar, you're just changing the tightness.
Right.
What about percussion? Drums, tabla.
Percussion usually involves a stretched membrane, like a drum skin. You strike it, the membrane vibrates.
Okay.
And again, the pitch depends on the physical properties. How tight is the membrane? How big is it? Tighter and smaller generally means a higher pitch because it vibrates faster.
Got it. Then there are wind instruments, flutes, trumpets, clarinets.
Right. With these, you're usually dealing with a column of air inside a pipe or tube.
So the air vibrates.
Exactly. You blow air across an opening or into a mouthpiece, and that gets the air inside vibrating. The length of that vibrating air column is key to the pitch. Think about a trombone slide, changing the length, or covering holes on a flute.
Okay. And reed instruments. Harmonium, mouth organ. What are reeds?
Reeds are typically thin, flexible strips, often metal or cane. In these instruments, air is blown across the reeds, causing them to vibrate very rapidly.
So the reed itself vibrates.
Yes, and the size and stiffness of the reed determine the pitch of the sound it makes.
Interesting. And activity 10, the one about making your own instrument, the jal tarang.
Yeah, the bowls of water. Striking bowls with different water levels produces different notes.
Why?
Because changing the water level changes how the bowl and the remaining air column vibrate. It's another way to see that pitch depends directly on the frequency of vibration.
Cool. And of course, we can't forget the sound source we're using right now, the human voice.
Absolutely. Activity 11, feeling your throat while you talk.
Yeah, you can feel that buzzing.
That's your vocal cords vibrating. They're inside your larynx or voice box. Air from your lungs passes over them.
And they vibrate.
When you talk or sing, yes. Muscles tighten them, and the airflow makes them vibrate. When you're just breathing, they're relaxed and open.
And we can change the pitch of our voice, too.
Right. By changing the tension and effective length of the vocal cords, tighter usually means higher pitch. It's quite an amazing biological instrument.
It really is. So guitars, drums, flutes, voices, it all comes back to vibration. Okay, let's shift gears slightly. What happens after the sound is made and travels? What about reflection? Sound bouncing off things?
Yes, sound reflection. It's actually very similar to how light reflects off a mirror. Sound waves can bounce off surfaces, too.
Okay.
The example in figure 3.18 with the ticking clock in the glass container.
Yeah, with the lid.
It showed that if you angle the lid just right, the sound can become much clearer. That's because the sound waves are hitting the lid and reflecting off it towards your ear.
So when I'm in a room, I'm not just hearing sound directly from, say, the radio. I'm also hearing reflections off the walls and ceiling.
Absolutely. You're hearing a mix of direct sound and reflected sound. In most normal-sized rooms, those reflections arrive so quickly after the direct sound that your brain usually merges them all together.
Why is that?
Partly because of something called persistence of hearing. Our ears kind of hold on to a sound for a tiny fraction of a second, about 0.1 seconds. If the reflection arrives within that time, we don't usually perceive it as separate.
Okay. But if the room is really big, like a gym or a canyon?
Exactly. Then the reflected sound has further to travel. If it takes more than that 0.1 seconds to get back to you after the original sound,
you hear it as a distinct echo.
Precisely. A clear, separate repetition of the original sound.
And animals use this, right? Bats.
Yes. Bats use echolocation. They emit high-frequency squeaks and then listen for the echoes bouncing off obstacles or insects. The timing and nature of the echoes tell them exactly where things are, even in total darkness. It's like seeing with sound.
That is amazing. So do all surfaces reflect sound equally well?
No, definitely not. Hard, smooth, dense surfaces are good reflectors. Think concrete walls, tiled floors, metal sheets.
Okay, and bad reflectors.
Soft, porous, or uneven surfaces tend to absorb sound energy rather than reflect it. Things like thick carpets, heavy curtains, acoustic foam panels, even furniture.
That's why recording studios have all that foam padding on the walls.
Exactly, to soak up reflections and prevent unwanted echoes or reverberation, which could make the recording sound muddy.
So an echo is that single, clear, reflected sound.
Mm-hmm.
And you need a certain distance for it.
Right. The sources calculated it for air. Based on the speed of sound, around 332 meters, and that 0.1 second persistence of hearing, the reflecting surface needs to be at least half the total distance sound travels in 0.1 seconds away from you.
Which works out to?
About 16.6 meters. So the total path source to reflector and back to source needs to be about 33.2 meters for a distinct echo.
Got it. And what about reverberation? You mentioned that.
Reverberation is what happens when you get lots of reflections bouncing around, arriving at slightly different times, overlapping. It's that lingering sort of wash of sound you hear in a large echoey space like a cathedral or an empty hall, multiple echoes blending together.
Okay. Now, this whole idea of sound reflection and echoes, it's used in technology too, isn't it? Sonar.
Yes, sonar stands for sound navigation and ranging. It's basically technological echolocation.
How's it used?
Oh, in lots of ways. Ships use it to measure the depth of the sea. They send a sound pulse down and time how long it takes for the echo to bounce off the seabed. They also use it to detect things underwater, like submarines, schools of fish, or shipwrecks.
like the bats and dolphins do naturally.
Exactly. And it's even used in medicine. Ultrasonography or ultrasound scans, that uses high-frequency sound waves and their reflections to create images of inside the body.
Wow. So how does the basic sonar work? Send out a ping and listen.
Pretty much. A transmitter sends out a pulse of sound waves. Those waves travel through the water, hit an object, and some of that sound reflects back as an echo. A receiver picks up the echo.
And the timing tells you the distance.
Right. You measure the time between sending the pulse and receiving the echo. Since you know the speed of sound in water, you can calculate the distance to the object. You just have to remember to divide the total travel time by 2, because the sound went there and back.
Makes sense. And the examples calculated sea depth and the distance to a hill using echo timing.
Yeah, they show how that simple principle, time, speed, distance, combined with sound reflection, has really practical applications.
Well, this has been quite the journey through sound. It feels like we've covered a lot of ground.
We really have. From the very beginning, vibration as the source of energy.
Right, needing a medium, solid, liquid, or gas to travel through.
And how the speed changes depending on that medium.
Then the difference between musical sound with its regular patterns and noise, which is more chaotic.
And looking at all the different sound sources, instruments, tuning forks, our own voices.
And finally, how sound bounces back reflection, echoes, and how we use that in things like sonar.
It's fascinating when you break it down, isn't it? Something we experience constantly, but there's so much science packed into every sound wave.
There really is. And it makes you wonder, doesn't it? How else are these principles being used? Maybe in designing concert halls for perfect acoustics, or how different animals have evolved unique ways to use sound for communication or survival. Things we didn't even touch on.
Absolutely. There's a whole world of acoustics out there still to explore. It definitely gives you something to listen out for.